Even though none of the group 13 elements react with hydrogen directly to form the corresponding hydrides, the chemistry of these compounds is well known, and it results especially interesting in the case of boron hydrides. Boron has a rich chemistry with hydrogen, forming combination with unusual stoichiometries and structure, and the number of these hydrides is so huge that it only exists in the case of carbon. This family of boron hydride is known as boranes, precisely from their analogy with alkanes. Around 50 neutral boranes and even more boranes anions of general stoichiometry BN-HM and BN-HMX- respectively are known. Boranes are interesting species considering that the shapes of the molecules are different from those of other hydrides, and the study of their bonding has required the expansion of the molecular orbital theory in order to explain their unusual stoichiometries. Additionally, their chemical reactivity is tremendously extensive, and although it presents some analogies to organic chemistry, the chemistry of borane is unique and quite different from that observed in organometallic and organic chemistry. Related to the structural feature of borane chemistry, one of the most unique aspects is that hydrogen atoms often act as bridge between neighboring boron atoms, as is shown in the simplest DIBORANE molecule, shown here in the screen. In the molecule, we can observe the presence of two hydridic bridge bonds, which means one bridging hydrogen atom between two neighboring boron atoms. This situation adds more complexity to this species. This new type of bond can be easily visualized in the simplest boron hydride diborane. Diborane geometry can be described as pseudo-tetrahedral around each boron atom, which present 4 bonds corresponding to an sp3 hybridization. 2 of the 4 half-filled hybrid orbitals of boron will be involved in bonding with the 1s orbital of the 2-terminal hydrogen atom, forming 2 normal 2-electrons bonds. The third single half-filled hybrid orbital overlap at the same time with both the empty hybrid sp3 orbital of the neighboring boron atom and the 1s orbital of the bridging hydrogen atom. This arrangement will result in a single orbital that encompasses all the 3 atoms, a cis-center bond called banana bonds. That results in an electron-deficient bond since only contain 2 electrons for connect 3 atoms. An identical arrangement forms the other BHB bridge. This situation generates, as a result, a weak covalent bond commonly known in terms of 3-center 2-electron bond. As a result, the bonding electron distribution of diborane will be as is shown in the following image. This structure only has 2 boron atoms, and therefore it is quite simple. But more complex boron hydrides are known, where the number of boron atoms is higher and they are arranged in the form of well-defined polyhedron. This cluster structure usually contains equilateral triangular faces of boron atoms. This type of polyhedron, in which every face is triangular, are commonly known as deltahedron, such as tetrahedron, octahedron, and so on. We can consider 3 common classes of boranes and borane anions, depending on the closed deltahedral cage arranged. There is a family called the closed cluster, where the boron atoms form a closed deltahedral cage. The generic formula is BN-HN2-. For example, here we present the octahedral structure of the dinegative anion B6H6-2-. The nido cluster, an open cage cluster derived from a closed deltahedron with 1 boron atom missing. The common generic formulas are BN-HN+4 or BN-HN+3. For example, B2X6, B5H9, and B5H8. The following image shows the structure of the B5H9 compound. As you can see, the structure can be seen as the result of removing a BH vortex from the closed structure B6X6 to form a square pyramid and adding 4 hydrogen atoms as the bridge between the boron atom of the base of the pyramid. In a similar way, we can generate the family of arachnocluster. An open cage cluster also derived from a closed deltahedron, but now with 2 boron atoms missing. The common generic formulas are Bn Hn plus 6 or Bn Hn plus 5, 1 minus. For example, B4H10 and B4H9, 1 minus, as is illustrated in the following figure. The structure of the different polyhedral borohydrides can be rationalized by a simple approach presented by Kenneth Wade in the 1970s. The so-called Wade rules allow us to predict the structure and shape of the different boranes. Although these rules were designed to predict borane structure, can be applied to analogous species in which there are atoms other than boron, such as carboranes or other p-block cluster. This approach starts by estimating the unit BH as the building block of the deltahedron, while the rest of hydrogens of the boranes will be attached as bridge entities between boron atoms to hold the cluster together. The BH unit will have 2 electrons assigned, which are known as residual electrons, while the rest of electrons in the structure, referred as skeleton electron pairs, are then calculated by the following set of rules. First, calculating the total number of valence electrons present in the compound, considering 3 electrons for each boron atom, 1 per hydrogen, and plus or minus the charge of the compound. Second, subtracting the residual electron, that is 2 electrons for each unit BH. And last one, dividing the resulting quantity by 2, which leaves the skeleton electron pairs which bind the cluster. According to the number of skeleton electron pair, we can establish the following prediction about the framework of the cluster. For a species with n boron atom, if we obtain n plus 1 skeleton electron pairs, the observed structure will be the regular polyhedron with n vertices. Such a structure corresponds to the closed cluster. If there are n boron atoms in a cluster with n plus 2 skeletal electron pairs, the framework is that formed by remove 1 vortex from the closed structure, that is, the nido framework. Likewise, when there are n plus 3 skeletal electron pairs from n boron atoms, 2 vertices are removed from the closed framework to obtain the arachnostructure. Finally, hypoboranes, which require n plus 4 skeletal electron pairs for n atoms of boron. For example, if we want to calculate the framework for pentaborane 9 and predict the structure, we should do the following simple calculation. Total valence electron 5 times 3 plus 9 times 1, which equals 24 electrons. Residual electrons will be 24 electrons minus 5 BH units, which contribute with 2 electrons. Then 24 minus 5 times 2, which equals 14. Skeleton electron pair will result to divide 14 by 2, which give 7 pairs. That is n plus 2 pairs, which means a nido cluster. The 5 boron atoms are seen to form a square pyramid where the 4 extra hydrogens atom bridge the 4 edges of the square open face. A similar treatment can be done for mixed element clusters such as carborane. Each element will contribute its valence electron to the total count of electrons, and it will have a terminal hydrogen atom forming a single unit, BH or CH, that counts for 2 electrons. For example, in C2B3H7, we have 2 times 4, 2 carbon atoms and 4 electrons, 4 valence electrons, plus 3 times 3, 3 boron atoms and 3 valence electrons, plus 7 hydrogen atoms. That equals to 24 electrons, from which 4 electrons are needed for the 2 CH units and 6 for the BH units. That leaves 7 skeletal pairs, and the structure should be a square pyramid in a Nido framework. Let's now to explore the reactivity of diborane compounds. Mostly of boranes inflames spontaneously or even explodes when mixed with air. Due to their fuel potential, the more stable of these compounds have been studied for application in higher energy fuels and propellants, for example, in satellite launching of rocket fuels. For example, the extremely exothermic reaction of diborane with oxygen liberates between 55 and 70 kilojoules per gram, while ethane, for example, offers only 40 kilojoules per mole when burned to carbon dioxide. To conclude the study of boranes, we are going to highlight the synthesis of the simplest compounds, that is, the diborane B2H6. This is accomplished on an industrial scale by the reaction of boron trifluoride with sodium hydride, and as is shown in the following equation. In the next section, we will study other important combinations of boron, such as borides and boron halides.